Dear friends, in previous class we discussed about the Liouville's function. It is denoted by lambda n and is defined as lambda 1 equals 1 and lambda n equals minus 1 power a1 plus etc. plus ak when n equals p1 power a1 etc. into pk power ak. And also we already show that lambda is a completely multiplicative function. By using these properties, we prove a theorem. For all n greater than or equals 1, sigma d divides n lambda d equals 1 if n is a square, 0 otherwise. Moreover, lambda inverse n equals modulus of mu of n. This is our requirement. How to prove this one? So its proof is, for its proof, let g equals sigma over d divides n lambda. Let g of n equals sigma g of n simply. Let g of n equals sigma over d divides n lambda. Clearly g is multiplicative. Why? Because lambda is completely multiplicative. Moreover, what about g of mn? G of mn equals sigma over d divides mn lambda d. Here d is of the form, d is the divisor of mn and d is of the form ab. Here d is of the form ab where a divides m and b divides n with a and b are relatively primes. So according to this argument, what is g of mn? G of mn equals sigma over a divides m, b divides n lambda ab. That equals sigma over a divides m, b divides n, lambda ab means lambda a into lambda b. So that equals sigma over a divides m lambda a into sigma over b divides n lambda b. So that is g of m into g of n. Hence g is multiplicative. Agreed. So we define g of n equals sigma over d divides n lambda d. Then we show that and we see that g is multiplicative. Agreed. G is multiplicative. Now suppose n equals product I ranges from 1 to k pi power a. So what is g of n? Clearly g of n equals g of product I ranges from 1 to k pi power a and g of product I ranges from 1 to k pi power a. But what is g? G is multiplicative, hence it is product I ranges from 1 to k, hence it equals product I ranges from 1 to k g of pi power a. Agree? So now what about g of n? Sigma d divides n lambda d. So what is g of p power a? G of p power a means it is sigma over d divides p power a lambda d. D divides p power a means the divisor of p power a. So when d divides p power a, the divisor of p power a are 1, p square, etc. p power a. So these are the divisors of this p power a. So that equals sigma over d divides p power a equals lambda d. So that equals lambda 1 plus lambda p plus lambda p square plus etc. plus lambda p power a. Agree? Now that equals, it is 1 plus minus 1 plus and so on. So it equals 1. It equals 1 when a is even. Equals 1 when a is even. 0 when a is even. When 0 when a is odd. Okay. Why? Why it is even and odd? Why it is 0 and 1? With respect, according to a is even or odd? Means when a is odd, what happens? A odd means suppose d divides p cube, sigma over d divides p cube of lambda d. So the divisors of p cube are 1, p square and p cube. Okay. So it is lambda 1. What is lambda 1? 1 plus lambda p minus 1 plus lambda p square means p and p. So it is 1 plus lambda p cube. It is minus 1. So it is 0. So when otherwise it is even, d divides p power 4. So 1 p square p cube and p power 4 are the devices. Then there is a 1 remains. So it is, we can conclude that lambda p g of p power a equals sigma d divides p power a lambda d, that equals 1 when a is even, 0 when a is odd. That means if any exponent a is odd, then if any exponent a is odd, then g of pi power a equals 0. If any exponent, if all exponent a is odd, then g of pi power a equals 0. If all exponents a are even, then g of pi power a equals 1. That means when any exponent a, all exponent a's are odd, so g of pi power a equals 0 means what is pi power a? That is n. So the g of n equals 0. So here when it is even, it is g of n equals 1. Agreed. So means g of n equals, that means g of n equals 1 when n is a square, and g of n equals 0 otherwise. G of n equals 1 when n is square, g of n equals 0 otherwise. What is g of n? That is sigma over d divides n lambda d, that equals 1 when n is a square, equals 0 otherwise. So the first part is finished. Agreed. Now to prove the second part, lambda inverse of n equals modulus of mu of n. How to prove this one? Lambda inverse of n equals modulus of mu of n. What is lambda? We already showed that lambda is completely multiplicative. Lambda is completely multiplicative. For every m and n, so we have lambda mn equals lambda m into lambda n. It is already proved. So, by the Mobius inverse formula, what is lambda inverse of n? Then lambda inverse of n equals some mu of n into lambda. F inverse n equals mu of n into f of n when f is completely multiplicative. By using that argument, lambda is completely multiplicative, that implies lambda inverse of n equals mu n into lambda n. Yeah. Agree. Now, mu n into lambda n means, suppose n is a square factor. What happens here? Suppose n has a square factor. N has square factors. If n has a square factor, what happens? What about our mu of n? If n has a square factor, by definition, mu of n equals 0. Agree. If n has a square factor, mu of n equals 0. Therefore, the product mu of n into lambda n equals 0. Okay. If n is free from square factor, means n equals p1 etc. pk. p1 into p1 power a1 etc. pk power ak. All a's are 1. That is n equals p1 etc. p1 into p2 into etc. into pk. Then what is mu of n here? Here mu of n equals minus 1 power k. Agree? Minus 1 power k. What about lambda n? Lambda n equals minus 1 power 1 plus etc. plus 1 k times. That equals also minus 1 power k. So when n is free from square factor, we have mu of n equals lambda n. Agreed? So what about lambda inverse n? You can replace lambda n by mu of n. So it is mu of n into mu of n. So it is mu square of n, square factor, mu square n, that equals modulus of mu of n. That is always positive. So the inverse of Liouville's function, lambda inverse n equals modulus of mu of n. Agreed? This is immediately followed from Mobius inversion form. This immediately followed from this argument. When lambda is completely multiplicative, when f is completely multiplicative, f inverse n equals, not Mobius, when f is completely multiplicative, then f inverse of n equals mu of n into f of n. Here lambda is completely multiplicative, so lambda inverse n equals mu of n into lambda. Enough. So this is the Liouville's function. Now we will define another arithmetic function, that is the divisor function. It is known as divisor function. What is a divisor function? For a real, it is defined as, the divisor function is defined as, for real or complex alpha, for any real or complex alpha, and for an integer n greater than or equals 1, then the divisor function is defined as sigma alpha of n equals sigma over d divides n d power alpha. That is the sum of the alpha the power of its divisors. Sigma alpha of n, that is the divisor function. It is defined as the sum of alpha the power of the divisors of n, that is sigma d divides n d power alpha. Okay. Now, what about u star n? What is n power alpha? We know that n power alpha of d equals d power alpha. Okay. What about u star n power alpha? U star n power alpha equals n power alpha star u, because star is commutative, that is the reciprocal product, equals sigma over d divides n power alpha of d into u of n by d by definition. What is n power alpha of d? It is n power alpha of d is d power alpha, that is sigma over d divides n d power alpha into what is u of n by d? U of n by d equals 1. So that equals sigma d divides n d power alpha, that is sigma alpha of u. So we know that sigma alpha equals u star n power alpha. Sigma alpha equals u star n power alpha. So this is the another result. The divisor function sigma alpha of n equals sigma over d divides n d power alpha. It is nothing but sigma alpha equals u star n power alpha. Agreed? Clearly, the sigma alpha is a multiplicative function. Why? U is a multiplicative function. N power alpha is a multiplicative function. The Dirichlet product of, we already showed that the Dirichlet product of two multiplicative function is multiplicative. Hence, u star n power alpha is multiplicative. Hence, sigma alpha is multiplicative. The Dirichlet product of two multiplicative function need not be completely multiplicative, but the Dirichlet product of two multiplicative function is multiplicative. Here, u and the n power alpha are multiplicative function. Hence, the Dirichlet product is multiplicative. Hence, u star n power alpha is multiplicative. Hence, the divisor function sigma alpha is multiplicative. Okay. Now, what about sigma 0 of n? Sigma 0 of n. Sigma 0 of n with respect alpha is a complex number, complex or real or complex number. According to your construction, alpha, by the choice of alpha is real or complex. Hence, when alpha equals 0, what is sigma 0 of n? Sigma 0 of n equals sigma over d divides n d power alpha, means d power 0, that is 1. Agreed? So sigma alpha of sigma 0 of n equals sigma 0 of n equals sigma over d divides n 1. Sigma over d divides 1 means it is the number of divisors of n. Number of divisors of n. Means sigma 0 of n equals, sigma naught n equals, it is d of n. The number of divisors of n means it is d of n. What is sigma 1 of alpha? Sigma 1 of alpha equals sigma d divides n d power 1. That is the sum of the divisors. It is the sigma d divides n d means it is the sum of divisors of n. So sigma 0 of n is number of divisors of n. Sigma 0 of n is number of divisors of n. And sigma 1 of n equals sigma 1 of n and alpha. Sigma 1 of n. Sigma 0 of n is number of divisors of n. And sigma 1 of n is sum of divisors of n. There is a difference. Sigma 0 of n is the number of divisors of n, and sigma 1 of n is the sum of divisors of n. When n equals p1 power a1, etc., pk power ak, what about sigma alpha of n? Then sigma alpha of n equals, here sigma alpha of n is sigma alpha of p1 power a1, etc., pk power ak. Okay, but sigma alpha is a multiplicative function. So it is sigma alpha of p1 power a1, etc., into sigma alpha of pk power ak. Sigma alpha of n equals then sigma alpha of n, when n is the product of powers of primes, then sigma alpha of p1 power a1, etc., sigma alpha of pk power ak. Okay. Now, By using this definition, we prove a theorem. For the divisor function, let sigma alpha of p theorem, sigma alpha of p power e equals p power alpha into a plus 1, p power alpha into a plus 1 minus 1 divided by p power alpha minus 1 if alpha differs from 0. Alpha equals 0, what happens? Does not exist. Equals a plus 1 if alpha equals 0. A plus 1 if alpha equals 0. This is the theorem. Sigma alpha of p power a equals p power alpha into a plus 1 minus 1 by p power alpha minus 1 provided alpha differs from 0, a plus 1 provided alpha equals 0. How to prove this one? Come to the proof. First, suppose alpha differs from 0. Later, alpha differs from 0. Then what about sigma alpha of n? By definition, sigma alpha of n is sigma over d divides n, d power alpha. So sigma alpha of p power a equals sigma over d divides p power a, sigma over d divides p power a, d power alpha. Okay. But what are the divisors of p power a? Divisors of p power a are, the divisors of p power a are 1, p, p square, etc., p power a minus 1, comma, p power a. These are the divisors of p power a. So what about sigma alpha of p power a? Sigma d divides 1 of d power alpha. Sigma d divides 1 of d power alpha. That is 1 plus, if it is p, sigma p divides p power a. Okay, so it is d means it is p power a. Sorry, it is p power alpha. Then p square, it is p square all power alpha means p power 2 alpha plus etc. plus it is p power a alpha. The divisors of p power a are 1, p square, etc. up to p power a. Then when d equals 1 divides p power a, so it is 1 power alpha 1. When d is p, it is p power alpha. When d is p square, it is p power 2 alpha, etc. It is p power a alpha when d is p power a. Okay. So what about this one? Come to the sum on the right side, which is nothing but a geometric progression or geometric series with a equals 1, common ratio r equals p power alpha, and then n, here n is a plus 1. How many terms are there? There are a plus 1 terms. So 1 plus p power alpha plus etc. p power alpha a alpha is nothing but a geometric series with a common ratio p power alpha. First term is 1 and the number of terms is a plus 1. So what about Sn? We have Sn equals a into r power n minus 1 divided by r minus 1 provided r greater than 1. So here S a plus 1 equals, here n is a plus 1, it is a means 1, r means p power alpha, so p power alpha is p power alpha into n. R is p power alpha all power n minus 1 divided by r means p power alpha minus 1. What is alpha? What is n? A plus 1, that is p power alpha into a plus 1 minus 1 divided by p power alpha minus 1. When alpha differs from 0, sum of s of a plus 1 or sigma alpha of p power a is nothing but p power alpha into a plus 1 minus 1 divided by p power alpha minus 1. Okay. If alpha equals 0, what happens? If alpha equals 0, then sigma 0 of p power a, sigma alpha of p power a means sigma 0 of p power a. Sigma 0 of p power a means, what is sigma 0 of n? It is d of n. We also know that, we see that sigma 0 of n equals d of n, the number of divisors of n. So sigma 0 of p power a equals d of p power a. That means the number of divisors of p power a. How many divisors of p power a are there? 1, p square, etc. p power a are the divisors of p power a. Means there are a plus 1 divisors. So d of p power a is number of divisors of p power a, that is a plus 1. Hence sigma 0 of p power a is a plus 1. That's immediately followed from sigma 0 of n. Okay. So this is an important theorem about this divisor function. Now there is only other result. For n greater than or equals 1, we have sigma alpha inverse of n equals sigma over d divides n d power alpha mu of d power alpha into mu of d into mu of n by d. So the result is, the proof is so simple, that is depends upon sigma alpha. What is sigma alpha? We know that sigma alpha equals n power alpha star u. Okay, so sigma alpha is multiplicative. So sigma alpha inverse equals n power alpha inverse star u inverse. But what is u inverse? But we know that u inverse equals mu. Since n power alpha is completely multiplicative, n power alpha inverse equals n power alpha of n into mu of n. n power alpha inverse equals mu of n into n power alpha of n. By using these ideas, you can immediately prove that sigma alpha inverse of n equals sigma over d divides n d power alpha mu of d into mu of n by. So this is the end of this chapter.